Okay, well, good morning, everyone. I'd like to welcome you to our T-CAIREM speaker series. My name is Mamata Bhatt, and I'm a partnerships lead for T-CAIREM. So it's my pleasure to welcome you to this special speaker series talk today by Dr. Phaneendra Yalavarthy from the Indian Institute of Science. He leads important initiatives in healthcare AI there. And his talk will be entitled Navigating Challenges in AI-Based Ultrasound Image Analysis. Now, before we start, I have a few items to take care of, including our land acknowledgement. We wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Wendat Nation, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. The Temerty Centre for AI Research and Education in Medicine at the University of Toronto has been made possible by the generous donation from the Temerty family. T-CAIREM is an interdepartmental center that serves as a focal point for collaboration among healthcare providers, trainees, researchers, computer scientists, engineers, and industry. Our goal is to transform health through AI. Just one note to our attendees today. Please use the Q&A function in Zoom to submit your questions for today's speaker. He will address them during the discussion portion of this webinar, which will be moderated by our trainee representative in the education pillar, Abhishek Moturu. So now I'll proceed to introducing Dr. Yalavarthy. We're very pleased to have Dr. Phaneendra Yalavarthy presenting today. He is an alumnus of Dartmouth College, graduated with a PhD in 2007, and currently serves as the director of the Translational AI for Networked Universal Healthcare, TANUH, the AI Center of Excellence in Healthcare at the Indian Institute of Science, IISc, Bangalore, India. He's also a professor of data science at IISc in Bengaluru. I'd like to invite Dr. Yalavarthy to start his presentation. And as mentioned, at the end, we will have a question and answer session moderated by Abhishek. So the floor is yours, Dr. Yalavarthy.
Okay, thanks. Thanks, President Mamata Bhatt. I'm pleased to be here. What I'm going to do in the next 35 to 40 minutes is to just, not that I have all the solutions of navigating the challenges of AI-based ultrasound image analysis, but I'll just try to point out that what we have done to a larger extent. So with the short note, I think I'll get started. Again, a lot of this work is not really done by me alone. We have a couple of good collaborators, couple of good students, couple of good postdocs who have worked on it. The ones in the pink color are the ones which I should definitely acknowledge because they were part of the whole study as well. And I also should acknowledge that I've received quite a bit of funding from the partners as well. So having said that, I just thought that it is a good opportunity for me to introduce IISc, those of you who doesn't know it. In fact, if you know IISc, this might be a little bit repetitive. But IISc is considered as, has been on the #1 university or research institute in India for more than, I will say, 50 years. I'd say for the past 5 decades, it has been the #1 university or research institute. And then we are located in southern part of India, and we are located in what is called the Silicon Valley of India, which is in Bangalore. And we have a 400-acre campus, and anytime you are on that side of the globe, please do visit us. It's a very nice green campus as well. So with that short thing about the institute, I thought that I'll just start off on, just as an outline, I would like to start off on what is the current challenges on the ultrasound image analysis is. And in that, I would like to go on with what are the AI challenges we have. And then just showcase you one of the work we have done in the ultrasound imaging, which is on the median nerve segmentation. And then I'll also show you some demo of how we have applied it in real time. And then leave you with some topics for future research or what we think we could expect as a road ahead. So now let me just start off. And those of you who doesn't want to listen to the whole talk, I'll say that most of the material is from these two papers we have published recently. And if you want to read those papers, they are here. One of them is in the TUFFC, and another one is in the medical physics. And both of them are authored by my students and postdocs. So let me start off on a high level. And this is the PubMed search I did. Then I just said that, if at all we search for papers modality wise, like I search for MRI, I search for CT, I search for X-ray, I search for ultrasound on the PubMed, how many papers do I get? So the one in the red is in the ultrasound. Roughly, I will argue saying that number of papers on the ultrasound, X-ray, and even though on the MRI side, it's much more because of the comprehensive nature of what MRI provides. But research-wise, almost all the modalities are in the same ballpark numbers. So at least what is existing in the PubMed. And then you ask the question now that AI is on the trend. Now you ask that how many papers are there for AI being applied to these modalities? What you'll observe is that roughly MR has about 30,000 papers, and CT has about roughly 28,000. X-ray is slightly on the lower side, about 20,000, but ultrasound tend to be the lowest among all. So almost, I'll argue saying that it's 50% of what is the average of rest of the modalities is. And that is for a reason why there are not that many AI papers in ultrasound. And by nature, ultrasound is cheaper. I mean, of course, by nature, X-ray is also cheaper. But ideally, I would expect X-ray and ultrasound to have the same number of papers. Like what we have seen here, ultrasound and X-ray tend to have similar numbers altogether. But in the AI world, it is almost half of what exists for X-ray. And I'll tell you the reasons for it in a minute. But that's the primary challenge we have. And those of you who doesn't know ultrasound imaging, ultrasound is what we call it as a reflection modality. So where you have a transducer which is actually sending the sound waves, and then the same transducer also acts as a detector, what gets reflected out of the body or the organ. And typically that's why we call it as reflections, because you are measuring what is called as an echo or a reflection of the sound waves. Now again, this goes back into the computer, and then what you see is a ultrasound image, which is essentially what we call it as compressibility of the tissue, or you can also say that what is the softness of the tissue, because mechanical waves are compressing the tissue as well. So in a very broad sense, from the image analysis point of view, ultrasound has two resolutions. So resolution is ability to distinguish two structures which are side by side. So one is called as axial resolution. So the axial resolution means that it is along the beam path, which is, you can see these green ones, right? So the axial resolution is really constant, doesn't matter where you put your tissue, whether you are here or whether you are far away or whether you are near field, doesn't matter what is your distance from the ultrasound to the organ is, it gives you same resolution. We call this as constant. And then if you look at the lateral resolution, which is kind of 90 degrees opposite to the beam, so which you see these red dots. So now it all depends on where you are. So at the near field, you have the highest resolution. At the far field, you have the lowest resolution, because the sound wave tends to diverge. So depending on what is the distance from the ultrasound transducer, your resolution keeps changing. So at least laterally it keeps changing. So this is one of the fundamental problem of what you observe structure to, whether they are near to your ultrasound or far away from the ultrasound. In a broader sense, the far away it is from the ultrasound transducer, it has a worse resolution. So ultrasound is not really that good in terms of imaging something which is at depth. So unless you use frequencies which are on the lower side. Then if you're using frequencies on the lower side, then you have this axial resolution being quite bad as well. So in a very simple sense, we call this lateral resolution being diffraction limited. So that means that deeper regions have less resolution. Axial resolution largely depends on the transducer, system bandwidth, and pulse energy. So these are all what we call it as beam characteristics. And most of the structures you see are also plagued by something called as a speckle. So that is, the speckle is a brightness variations. So for example, here is where I'm really showing you what is the median nerve looks like, a nerve looks like. And then if you see in the red one and compare it with others, that structure is very hard to distinguish. So this we call it as absence of clear boundaries. So obviously you are imaging everything as a soft tissue. You don't have a very clear boundaries to distinguish it. And because of that, the automated algorithms like which are AI driven tends to be very, very challenging. And then in terms of temporal resolution, if you're because most of the ultrasound is done in a cine mode, so they're all like videos. So there is also could be speed of sound variations that might come into it. The reason is that we assume that the ultrasound speed is 1540 meters per second, and that's how the whole imaging is done. But in reality, there is a lot of variation in the speed of sound, which is underlying tissue as well. So that is just to give you why ultrasound imaging tends to be a little difficult. And the characteristics itself are plagued by a lot of this. So now, again, what happens in the AI solution is because AI is purely data driven, as you all know, one of the biggest problem is that ultrasound is always what we call it as bedside monitoring or point of care modality. So typically archival of images is not very, very common. So if it is a CT, MR, typically people use packs to store it. So ultrasound images storage is not very, very common. And the images itself are tend to be little low quality because of the point of care, and you are trying to do it not in a very, very controlled environment, because of which the images tends to have low quality. And most of the image analysis that gets done on the ultrasound is what we call as qualitative. So that means that on the fly they do this analysis. They really don't really do so many measurements as such. Even when they do measurements, they freeze the frame and then do the measurements. So, and then this is what we call it as has been the challenge is that how do you interpret something? For example, I spoke about speckle, which is variation in the brightness. There is a group of people who argue that speckle is a noise, and there is another group which says that speckle is actually the signal which is present. So now again, it depends on how do you interpret it. And more importantly, this is what has been plaguing a lot is that what is the plane you use, what is the anatomy to be imaged is typically determined by the sonographer or whoever is imaging that. And that means that you may not have consistent scan as well. So that means that you may not get the same plane every time you are expecting like a CT. Now you have a very good structural way of getting it. And then common scanning method, I already mentioned that is a cine ultrasound. So that means that typically it is 40 frames in a second. So that means that you also have low signal to ratio. And those of you who are familiar with AI, when you don't have enough data, we apply something called as augmentation. And in the augmentation world, one of the things you can do is a flip. So that means that you put what is top to the bottom and bottom to the top. That augmentation is not really applicable in the ultrasound because you only image from the top to the bottom. There is no way you can go inside and then do that. So it's not possible. So that means that not all transforms are applicable. So in a nutshell, what I wanted to mention is that ultrasound has AI solutions are not being developed so many in the ultrasound because there is a very poor image quality. So because of that, that brings it a challenge for the AI. And the echogeneticity of the structures, not having this very clear boundaries between the organs or structures is also a challenge. And more importantly, most of the ultrasound is a point of care. That means that there is no cloud support to it or there is no storage support to it. And then most of them use it for on-the-fly diagnosis. So if at all you have an AI solution, it should also be able to do on the fly. So that's the fundamental thing. That's why if you develop an offline diagnostics or offline analysis of ultrasound, that may not be really useful as well. So now again, I want to come back and then this is something which is my favorite slide in terms of where do you have value for the automated analysis. So for example, let's say that in this case, what we are seeing is that actually they are imaging the this what we call it as a hand, and then this is a hockey stick type of probe where they are trying to image the median nerve in this case. So that median nerve is the structure which we are interested in. And if you are only doing some kind of median nerve detection, so the value chain for that is quite low. And if you are really segmenting out the median nerve, in my view, this is going to be very low. What you build on top of it after you have segmented, quantified it, what you build as an automated workflow has a little bit more one rather than doing it in the offline one. And then, of course, if you can provide with all this automated workflow a differential diagnosis, so that I think is the top of the pyramid where you will have, that is the support which most of the clinicians look for. So what I am showing is that, we have taken it, pushed the envelope to get into the automated workflows. Today, most of the AI tools fall into this kind of category, which is within the green, which is segmentation, visualization, and quantification. So they are able to do quantitative imaging. They are not really in the decision support tools as such. So that is what we wanted to build. And that is what I'm going to showcase as well in this talk. So the problem, so let me get into the problem, and then this is our lab work. So far, I have described only what is ultrasound challenges are and where does the automated analysis lie in. So this is one of the problem which we wanted to solve is that we are interested in median nerve segmentation in ultrasound. Why median nerve? Because median nerve is the sensory and motor nerve of the arm, and every arm movement is facilitated by the median nerve, and any hand movement is by the median nerve. And it passes through a narrow passage called as carpal tunnel. So that is near the wrist. So this is the carpal tunnel. And then if you have an injury to the tissues within the tunnel, that means that if you have injury to the wrist, so then what happens is that it presses the median nerve. So now when it presses the median nerve, that is what is known as carpal tunnel syndrome. So the CTS prevalence, as such, is 1 in 1,000. And if you are using a keyboard, there is a 20% chance that you also develop carpal tunnel syndrome. And what is the what we call it as standard test people do? So they do electromyography, or what is known as nerve conduction test, and it has very good sensitivity, but its specificity is very poor. And if at all you want to know if somebody is getting treated for a carpal tunnel syndrome, if you want to look at the progression of what their syndrome is, it's very hard to do it in the electromyography. So typically people do ultrasound on this and then try to determine what is the cross-sectional area of the median nerve. So, and I will show you those examples. If cross-sectional area is on the higher side, you say that that is severe CTS. And a typical cross-sectional area you expect, at least at the wrist level, is around 9 millimeters square. So that is what we are interested in. Anything above it, you say that they are CTS positive, whether it is mild or severe, depends on how much has been come out as a cross-sectional area. And now, how do people know what is a cross-sectional area? Typically, what they do is that they keep scanning it and they freeze the frame and they try to get that dimensions into this. So what we wanted was a completely an automated solution for it. So what we did was we put this, and of course India is a IT hub. There are a lot of patients who come with carpal tunnel syndrome, because I told you 1 in 5 have, if you are using keyboard, have this carpal tunnel syndrome. So they come, and we also did this study as a part of the Astra CMI hospitals. We collected about 100 patients' data, and each one is a 17 seconds video. And the number of frames which are there in each second is around 39 frames. So that leads us to around 624 frames. And then we have obviously done what is called as anonymization of this data. We removed it all the PII, personally identifiable information from these frames. And then we have asked a neurologist to painstakingly do this. Remember, that is around 62,400 frames to be annotated. So the neurologist, who is Dr. Lokesh, has painstakingly done all the labeling for us. And then, we had each patient has these labels of what we call it as median nerve and what is non-median nerve region. And then we generated this CSV files for the data process. which we use it in the data loaders for the AI models. And the data as such was collected from what is called as hockey stick probe, and it was collected using a Philips CX50 machine. And as I mentioned that the frequency of the ultrasound that was used is 7 to 15 megahertz, and it can cover up to 3 centimeter depth. There were two depths we have used, 1.5 centimeter and 3 centimeters. And the mode we collected was B mode, and I already mentioned 39 frames per second. And then we collected 17-second video that is going from top of the wrist to the bottom. So now the first one, as I mentioned, we are interested in measuring the cross-sectional area, and we wanted to do it. Given a frame, can we segment out the median now? And from here, if I know the number of pixels within this region, within this blue contour, I know what is the area occupied by each pixel based on what is the ultrasound depth I am using. I just compute that CSA. If I know the number of pixels in it, we call this as a mask. If I know the mask, I can really multiply it and then get it. So currently, it is a normal median now, or those which are negative for CTS. So they all have a cross-sectional area of less than 9 millimeters square. And we call it as mild carpal tunnel syndrome if it is between 9 and 11. And if it is greater than 11 mm square, we call it as a severe CTS. So we are interested ultimately in the cross-sectional area of the median now, because the markers are very clear. Based on the quantitative metrics, you can really calibrate the carpal tunnel syndrome. So again, if you are interested in the deep learning part of it, we have used a loss function, which is a combination of cross entropy, binary cross entropy, and structural similarity. And we have used a batch size of 16. The number of epochs we ran are 16. We have used 80 patients data for training, 10 for validation, and 10 for testing. And then all the images were captured at 3 centimeter, even though I will show you some examples of what we have done when we were testing it on 1.5 centimeter as well. So initially, when we started this work, we started using what is called as vision transformer. And the vision transformer is the same architecture which like ChatGPT or large models use. And then all we did is that we looked at the processing, and then it was given all the frames. And of course, we transformed it to segment out the median now. And the results were quite good, and it was also one of the first paper which has applied the transformer to ultrasound median nerve segmentation. And again, what has happened is that you can see here. So this is in the real time. I'll show you some of the real time as well later. But the one which you are seeing in the red is actually the ground truth that is marked by the radiologist. So the one you are seeing as a green is what is segmented by our algorithm. So that is our AI algorithm, which is based on the vision transformer. And we compared with rest of the AI algorithms that exist in the literature. So like UNet, UNet++, SIMS UNet, a trans UNet. So one of the things I want to point out is that the number of parameters which are required and what is the average dye score. Dye score is what is the similarity of the contours and the masks between what is marked by the neurologist or the radiologist versus what is our AI algorithm is giving. When you see a number like 0.95, that means that it is 95%, the mask is overlapping. So one of the things which we were able to prove was that, at least with the algorithms that exist, so near to the wrist, we call it as proximal to the carpal tunnel, almost all algorithms were able to give a good result, right? Like for example, if I'm comparing this second best one, and ours is not so far away from it. It's more or less giving you. That means that the moment we go far away from the wrist and then go a little below, what was happening is that we are at least, I will argue, saying that at least we are 5% better than what is existing in the literature. So that means that the more, also what happens is the median nerve goes deeper as we move away from wrist. So that is one of the reasons why we call it as it is a very challenging problem. In the first second, we get very good accuracies. anything beyond first second becomes a very challenging for most of the algorithms. Whereas our vision transformer was able to give very good accuracy, around 83% accuracy, even in those challenging cases. So I thought that we have solved the problem, and then we published this work. But then the neurologist whom we work with, Dr. Lokesh, said that no, this is not the end all. Can you really deploy it? And then while scanning, I would like to see the segmentation and also show me the cross-sectional area. So that became a challenge because this is not really can run in real time. So in some sense, if you have to process it in real time, we require what we call as more lighter model which can run on it. So then we went back, and then we could not use the vision transformer because it's using almost 75 million parameters. So we went back to the board, redesigned our algorithm, or redesigned the architecture. We came up with a new architecture, and then we use the backbone of what we call it as U square net, and then combined with half units so that we can do what is called as multi-scale feature fusion with having very less number of parameters without compromising the accuracy. So what our new network has, so remember the original network had about 75 million parameters. So now what we were able to do is that bring it down to about 1.23 million parameters. A number of flops were less. We were able to process 43 frames per second. Right. So now that is a big jump for us. Remember, for 1 second, we were looking at about 39 frames per second. So this 43 is a very good number for us. That means that we can deploy it in the real time. With the additional overhead of processing and other things, we thought that then this becomes a very real time. So then we started implementing it, and then we thought that, could we come up with something? And before we do that, we did somewhat what we call it as a benchmarking. So what has happened is that, remember, I showed you this 95% and 83%. So that is the same numbers we were getting using even our very lightweight model. So it has turned out that we didn't compromise on the accuracy part as well when we did this. So we tried to deploy it, and then this is something which I told you, right? Remember, all the data we collected was at 3 centimeter depth, and that is what the model is trained. And even when we applied at 1.5 centimeter, it was able to give you a good, segmentation result as well. And as I mentioned, anything above 11 mm square, this is a cross-sectional area. We call that as a severe CTS. So that is what you are able to see here. So this is where we have a mild CTS. Anything above 9, we call it as mild CTS. That is what you are observing here. So this is the median now you are seeing. So now how do we implement in the real time? So now Philips CX50, ideally we should go into the software and then try to put it there. But we did not want to disturb what is existing in the clinical. So what we did was, we call this as a parallel screen. So we put another laptop, which is parallel to what is there in the Philips CX50. And we had connected a DVI to HDMI interface. So this is a DVI cable which we connected, and we connected to a frame grabber. Frame grabber is the one which captures whatever is coming out here. And then we try to process everything and display it here. This becomes a little more clearer when I show you the next one. So this is how it looks like. This is also on a push cart. We put it as a parallel screen. And whatever you see here on the Philips CX50, the same thing is here. But except that I don't know whether it is visible to you or not, you have the cross-sectional area being displayed here. So that is in the green. At the moment it crosses 9 mm square, it will turn into red so that it can do it. And then again, with the same probe, same everything, and then we were able to really get this going in a real time. And I'll show you some video. Hopefully this video will play. I'm assuming that it will play. I'm not sure why it is not playing, but yeah. I don't know whether you are able to see this. So this is our parallel screen, which is just a simple laptop, which is running our AI algorithm, which is a very lightweight. And just, oops, I've done something. So this is another one where you are able to see this, right? So this is being displayed. The same thing is getting displayed here, and the cross-sectional area is right here. So while doing the scanning, we were able to showcase and then do the segmentation and give a mask as well, give a contour as well. And as I mentioned, this is also first time anybody has shown that this kind of capability of not really disturbing what is existing workflow and put it as a parallel screen and run things. So I mean, we were very happy with it. Now, right now, even though I said that we can do 43 frames per second on the deep learning algorithm, but there is a little bit of processing we need to do before. So that takes a little more time. So right now we are able to do 28 frames per second. So that's in the real time. Now, what is the road ahead for us? I mean, in my view, ideally we should do a big clinical trial. Right now we have done this only part of the what we are calling it as the Astra CMI hospital. And also now that we have the whole region which is automatically segmenting out all the frames, could we give an automated report how many frames were found to be above 9 mm square? So that is one thing. And if at all you think about it, the way we have done things is that at least in the ultrasound world, you collect the RF data. And the RF data becomes the image. And what we are doing is that we are processing the image, getting the features. That is, we have extracted, for example, in this case, median nerve. And once the median nerve is above 9 mm square, we are saying that that is CTS positive, or we are doing whatever actions which are supposed to be done. If at all you think about it, and if you think that everything is coming from the data, should we take this convoluted path of acquiring an image, getting into features, getting into actions? So if I have only the data, so that means that I don't need to do any processing from here itself. Can I get to actions? That means that while I scan itself, can I say that it is CTS positive or mild CTS or severe CTS? So that's a bigger question to ask. That means that we are talking about RF-based CTS detection. And whatever you have seen is what we call it as unidirectional. You give an image to it, and it will give you what we call it as the cross-sectional area. But there is no interaction that is happening between the model and the human. We call it as human in the loop. So could we develop a bidirectional interaction so that we can interact with the AI models also better? So I think more or less I'm done here. I think with that I will stop. And I'll be very happy to take up any questions, any comments of this. Thank you very much for patiently listening to me.
Thank you, Dr. Yalavarthy. It was really nice to see the whole process from like the problem definition to the model development, and then realizing the size of the model, and then pretty much getting the same accuracy as with a model with I think a 70th of the size. So that's really nice to see.
Yeah, that's true. That's true. And even though I have showed all the good things, all this work is 3 years of our work.
Right.
So that took us quite a bit of time for us.
Right.
These are not very easy things for us to do. But today, if you go to Astra CMI and then go to a neurology department, they call it as neurophysician department. They use our model on a daily basis.
Oh wow, amazing.
It's really deployed model it is.
If there's any questions from the audience, feel free to put them in the chat. I have a question to begin with. I was wondering, with the annotators, if you had mainly one person do each annotation, if there was any kind of inter-rater variability study that was done.
Now we haven't done that, so that's a great question actually. So ideally we should do that. Ideally, your label should be more accurate, and so ideally we should have done at least one more reader annotation, and then at least done a little bit of coherence kappa, and then at least identified that it is positively matching rather than negatively matching. So that's it. That's work in the progress, and we have that and want to create that as a gold label for us, so that our labels are correct. You are absolutely right.
I mean, from the videos, it seemed like it was like it overlapped pretty much exactly where the nerve was. But I was also wondering, sometimes there was like little other parts of the image that were highlighted. Would that happen if something looked like that nerve?
So actually, so I told you that there is an absence of clear boundaries, and I don't think human can make it out.
Yeah.
So sometimes it get confused on this, and then of course we can do a little bit of post processing and then say that there could be only one contour, not two contours, and things like that. But we didn't do it because the
Oh.
moment we start doing it, what happens is that we increase the processing time. And remember, we were opting for at least doing like 30 frames in a second. So any post processing you do, that is going to delay our thing. So that's why we did not want it to do any post processing.
Right. Understood. In the Q&A, we had a couple questions. Did your annotator develop carpal tunnel syndrome while doing the labels? That's a lot of labeling.
Oh, that's a great question. I like that. Yeah, maybe. But as I told you, we didn't do it in a single day. But it took almost because this is almost 64,000, 65,000 frames which he had to do. And it took about a year for us to get those annotations done. And then some of them in the end we became a little more smarter, and we only got the actual DL algorithm do it and then asked him to correct it. So we did more of corrections later rather than doing it from scratch. So it became a little faster, but having said that, it's painstakingly slow. I agree with that. And then I should thank Lokesh here, Dr. Lokesh, who has done that.
Was there any kind of um, kind of over time kind of labeling that was done, or was it frame by frame every time?
So no, it is over the time. So what happened is that we developed a platform using ImageJ. When you do it on one frame, at least for the next 10 frames, it populates it.
Right.
Such that you can correct it and then do it. But that we did little later.
Right.
So, but initial, I will argue saying that up to 20 patients, he has to do frame by frame painstakingly.
Right.
Because we were confident that there is a close matching for it, and then that's how we got it.
Right.
But I think I have to thank him here. He has done a tremendous job there. I think number crunching and doing model development, in my view, is little easier. Collection of this data and doing these annotations is what is hard.
And is there any age factor, BMI factor in relation to the 9mm size or even sex differences in carpal tunnel?
So obviously, I think somebody is asking a clinical question. I'm not a doctor, I'm not a clinician, but those are what is there existing in the literature. So, I mean, I think there is an age factor to it, if at all I remember correctly in the literature. But we didn't capture all that. We just took a benchmark and then tried to do that. And remember, our aim is not to develop a carpal tunnel syndrome diagnostics, right? We are only talking about median now diameter being our cross-sectional area being there. So our aim is not to diagnose people, but because we did not want to get into that kind of regime, we are only interested in computing the cross-sectional area. So in some sense, we computed and left it there. It is up to the clinician to make that. In some sense, our algorithm doesn't do diagnosis. It only gives you an image, quantitative imaging metric that you can use it in the diagnosis. That's what we have put. So we are only giving a finding rather than giving the diagnosis.
Right. And I was wondering, with the development of the UNet variant that you developed, I was wondering, were there parts of that original transformer model that you got inspired from? UNet, obviously, with a lot of data, I mean, with little data, it gives pretty good results. But what inspired you? How did you get inspired to develop?
So if you all you are looking for a lightweight version of the UNet, right? So see, for example, like UNet itself is 31 million. So if at all you are looking for what we call it as a lightweight version, there are only two options for you. In fact, I will argue saying that one is half UNet. So the other one is what we call it as U square net. We called it as U2net here. So we actually, what we did is that we found out that half UNet is the multi-scale feature fusion it will be able to do. So we took elements of the U square net and half UNet and then kind of combined both of them to do the feature fusion for us. Because what transformer does is that it kind of does feature fusion in a very efficient manner because of the attention mechanism it has. So in some sense, either we build an attention mechanism which is very lightweight, or we come up with a feature fusion which which is kind of an aggregation of all the features. So our embeddings has to be richer enough to, match the cross attention, what transformer typically does. So that's the whole thought process that went into the board, and then we did that. And by the way, this work was done by Venkatesh, who is a PhD student. I think he did a tremendous job here. And then he really went to the board and then did all this, came back and showed the embeddings and then showed that they are similar. And then we had a lot more confidence in terms of making that move forward with our deployment as well.
Amazing. I had another question. David asked another question. Are you planning on collecting more data to label and retrain your model for better dice scores, or are you happy with it clinically? Are there any patients that it doesn't work well on?
So I'm assuming that David is a clinician. So I don't think clinicians will be happy people, right? They want development and then everything. They want a perfect thing to be done. So we are still doing some collection of the data, not at the same level as we have done. But we want to do cross-validation. That's why I told you the clinical trial. We want to go beyond one center and then try to collect the data. Go beyond Philips CX50 is the scanner we have used. What happens if you use another scanner? So we want to do a little bit of, you can call it as cross-domain kind of one, which has some domain shift, whether our algorithm will be good with that or not. So those are all work in progress. But right now, at least in that center, they are very happy to use our algorithm, which makes me happy that we have developed something which they are using on a daily basis.
And with the human in the loop thing that you mentioned, what would the idea be while someone's using this, they're able to fix the labels or outputs a little bit, or would it be more on the diagnosis side?
So now, for example, like let's say that you have identified something about 10 mm square, and you want to know a little bit more about it, right? And at least showcase that frame in a better version. And then is it really is it even though I'm saying all nice things about 94, 95%, but still there is a 5% error to it.
Yeah.
So could it just showcase those frames which are trying to be positive for the CTS, and could they correct it to get a better sense of thing? For example, what we wanted to do was that most of the carpal tunnel syndrome patients go through some kind of physiotherapy. And then if they're coming back, could we do a change analysis from previous time to current time? So that's what we meant by human in the loop. So can it pull up the video which has captured previous time for the same frame and then showcase what has been the improvement? So did it went from like 11 mm square to like 10 mm square, or it did went from 10 mm square to something like 8 mm square? So that is what we meant by human in the loop. Right now, this is not very interactive. There is no way you can interact with it. You give an input, it gives you an output. There is no interaction that is happening. Primarily, we were looking for change analysis. Whenever I said human in the loop, we want to compare with the previous time point, whatever data exists, and then look at the trajectories of what has been the improvement, or whether it got worse as well.
Any other questions from the audience? If not, I have few little things I wanted to mention before we end. Wanted to thank Dr. Phaneendra Yalavarthy again for such a great talk, and for everyone for attending, for the questions. I want to mention two upcoming activities taking place at T-CAIREM this week. One, the trainee rounds are happening. These highlight innovative projects by emerging AI health researchers across Canada. And our third session is coming up on June 24th, which is tomorrow. We hope you can attend. And also, if you're a graduate or postgraduate trainee, or you know someone who is a graduate or postgraduate trainee at the University of Toronto, we're currently seeking a trainee representative for the T-CAIREM Advisory Committee. And details about both of these initiatives are on our website, and the deadline is July 6th. Thank you, everyone, again, for attending the fascinating talk, and especially Professor Phaneendra Yalavarthy for sharing his insights and experiences with it today on this topic.
Thanks, Abhishek. I would like to thank both President Mamata and you as well for hosting here. I think this is wonderful. Thank you very much.